Okay, we are on Unit 1, Day 4, and we are going to discuss graphical failure and error. Yes, these calculators you have are nice. They can do a lot for you, but every once in a while, okay? Every once in a while, things aren't quite what they seem with these calculators. For example, how about we graph this function right here, okay? Y equals 3 over 2x minus 5. All right? If I graph that, okay, and you'll look at the window I have here, all right? I want to see, okay, there's no bounds. If I graph that correctly, it should look something, and I adjust my window, something like this. All right? Something like this. Why does it look like this? Why does it look like it splits? Well, if we look at our table and notice the table I have here, it doesn't go by ones. It doesn't go from 0 to 1 to 2 to 3. I change it by 0.1, all right, by a tenth. Now, is there anybody who does not know how to change it? I'll show you real quick. You know what? I'm not even going to answer the question. I'm going to show you anyways. If I have not a problem, banging, turn this on, yeah, that's me. If I go to y equal, what was our fraction? It was, what was the numerator? 3. It is 3 divided by 2x minus 5. 2x minus 5. Okay? And if I graph this, now this is just a 10 by 10 window. Okay, I zoomed in on the presentation, but you still get the same picture here. All right? Now, if I look at my table, it currently starts at 0 and it moves by 1s. But on the presentation here, you'll notice it's by tenths, okay? So, if you want a table set, which is above window in blue, if I hit seconds, window, I'm going to start where I started. I kind of cover this up. It's 2.2. So if I start at 2.2, that's my table. That's where I want my table to start. No surprise there. And this little triangle, this means change. Okay? How do I want my table to change? I want it to change by 0.1s. That's it. That's it. Now let's look at our table. What do we notice happens at 2.5? There's an error at 2.5. There is an error at 2.5. So if I were to do this, that's what you would see in your table right there. There's an error at 2.5. How come there is an error at 2.5 with our function? Thank you very much. Why? How do we divide by 0? What are you talking about? You're right. Well, what was that? The denominator equals 0 when what? Thank you. These are your x values. If we make x 2.5, 2 times 2.5, this is the denominator, minus 5. That's 5 minus 5, which is 0, which we know is a big no-no for denominator. No. That can't happen. That's why we get an error. Does anyone know what happens on our graph when x is 2.5? So, if I look, here's 1, here's 2, here is 2.5 on the x-axis, correct? Here's our x-axis. What happens at 2.5? Notice the line doesn't appear to touch it. If I were to draw an imaginary line here at 2.5, see how the graph never touches it? It'll get closer. It'll get really, really close, but it'll never touch it. What's that called? It's my favorite, yes, my favorite math word of all time. You ready? Asymptote. There's a P there. I don't know why. Totes. In college, my college professor would always be like, there's an asymptote. And I'm like, what are you doing with it? What? I would say it's an asymptote. I would not pronounce the P. He's like, asymptote. I'm like, what is he doing? Is he on a list? What's happening here? Asymptote. And I would be sure not to say the front. I like to say the front, unless he would say that word, he would spit. Oh, asymptote. And then I would move back. And then I looked it up. I'm like, God damn it, there is a P right there. I've been saying it wrong all these years. But An asymptote, I can't do it. It just represents a value that your graph cannot touch. Okay, it goes up and down forever. And that yellow dashed line goes up and down forever. So as my function goes closer to 2.5 this way, it'll go up and go up. It'll get really close to the point where it looks like it just becomes that line. It's just so microscopically close, but it just never touches it. It can't. Why? Because you get an error at 2.5 if that was x. Your y would be undefined. Let's take a look at example number 2. All right? Now, I'm not going to graph this in the calculator. I want you to graph this in the calculator. Look at the function we're given. Y equals the square root of x minus 3. So I need to graph that in there and take a look at your table. Now, notice the table in the notes here. They do not change by tenths anymore. It starts at 0 and they change by ones. So I want you guys to go in and change your table back. You changed it before. Change it back. Okay, I want you to get used to having to do that if you need to. Might come in handy. So, I'll give you about another 10 more seconds to graph it. Not to look at the table, just to graph it. Yeah, if you didn't change it the first time, obviously you don't have to change the table back. Anyways, what does that graph look like? You can tell me, even with your fingers, like in the air. Yeah, that's okay. No, no, yes, no. You're drawing a circle. I don't know what that is. No, correct. Correct. It looks something like that. Okay? It looks something like that. Where it kind of starts at 3 here on the x-axis. That's 3, and it just kind of goes up and curves this way, like that forever. Now, if I look at my table starting at 0 and scrolling down, what do you notice? Yeah, you get an error for 2, 1, 0. What do you think would happen? Asymptotes. What do you think would happen if I? You hear that? You hear that? If I get sick, my daughter's been sick for like 2 weeks. My son kind of got it barely. My wife, like, I never get sick at home. And my wife tells me, she goes, "You're not." I said, "All the children." And I was like, "What do you mean? When you're not home?" I'm like, "When you're like, I don't know, like if you're making dinner or something, or if you're like on the computer doing something. What do you think's with the kids? What do you think? I just give them $20? I'm like, "See you later, kids." I'm like, "No, I actually watch out for the kids." So naturally, I'm a little offended. But if I get sick, that could be, I guess, a badge of honor. Anyways, what would happen in this table if I scrolled up? If I scrolled up to the negative numbers, -1, -2, yeah, you get an error still. How come? How come I get errors? Thank you. Say it again. Thank you. Just like our fraction, there were no 0 in the denominator, right? You can't have a 0 in the denominator. You get an error. Okay? And that's when x equals 2.5, correct? So if I look at this one, what's the restriction of radicals? I can't have negative numbers here. Can I have a 0 under radical? Question. What value of x would make this expression equal to 0? 3. 3 minus 3. Do I get a value at 3? Yeah. I do. It's 0. It's not undefined. So I can have a 0 under the radical. This represents what your x value would be. And this represents what would be under that radical. You know, when you take the square root of it, that's the y. Okay? So I can have 0 underneath the radical. So my x minus 3 has to be greater than 0. It can't be negative. It can be equal to 0, right? It can be greater or equal to 0. It can't be negative. Which means if I were to solve for x here, I can use any number that is 3 or bigger for my x. You know what this is called right here? When I describe all x values of a function? Your domain. That's your domain. That's all possible x values.
Oh, yeah.
Remember? Yeah. All possible x values are your domain. What's all possible outputs are y values? Domain and range. The y's would be your range. So, really, what my table does, these satellites here is my range. So my range could be anything 0 or bigger, correct? Yeah. My domain is my x values. So my domain, I can't say, well, Visca, that would be 0. No, it's wherever x has a value next to it. 3 or higher. That would be your domain. Is 3.1 in my domain? Yeah, isn't 3.1 bigger than 3? Yeah. Is negative 7? No, it's not, because negative 7 is not equal to or bigger than 3. In fact, if you put in the table negative 7, it'll give you an error. Quite simple stuff, children. Quite simple. Example number 3 of our graphical failure/error here. Okay, we have a function, y equals x to the power of 200, all raised to the 1 200. Now, can anyone, just by looking at that, algebraically explain to me why y would equal just x for all values where x is greater than or equal to 0? Kind of.
Because the next one is
Okay, that's what I think. I think that's where you're going. He explained the math behind it. All right. So, basically what I was told is, if I have x to the 200 raised to the 1 200, when we have an exponent raised to an exponent, we multiply exponents together, don't we? So that would mean I would have x to the 200th times 1 over 200. What is 200 times 1 over 200? It's 1. That would be 200 over 200, which is 1. That's x to the 1, or x. So I can just say y would equal x. That's legit. And what does the graph of that look like? What does the graph of y equals x look like? It's a diagonal line that goes which way? Up and to the right. This line right here, that's the line y equals x, correct? It is. Now, I want you, in your graphing calculators, to actually graph not y equals x. I want you to graph it this way in the calculator,
So
all right? Yeah, so you're going to put x to the 200th, and then raise that to the 1 200th. But look at the window I want you to use. Okay, I want you to go from 0 to 1 on the x, and 0 to 1 on the y. And I will do that. Well, I think I've already done it. And is the graph that we graph for b here, is that different than the graph of y equals x? Remember, you got to change your window. So, did you guys get that? Did you change your window?
You gotta change the window.
I got the straight line. The thing, that is what you're supposed to get. It's the same. But they stopped in the middle. I don't get why it started in the middle. Why don't start in the middle?
Ooh, interesting.
I saw what he did.
Oh, it's spinning like this.
Then we gotta talk to people.
All right. You should have gotten something like this. Okay, something like this. That is very different than y equals x, because y equals x continues to the origin like that. How come it stopped? Anyone have an idea?
You can check out the table, because if they didn't have errors for
I like your idea.
It might.
No, 4 or 5.
It might. But let's do it this way. When we saw this function here, x to the 200 raised to 1 200, we multiplied our exponents and got x to the first and just graphed this. Okay? The calculator does not do that. The calculator actually calculates whatever value to x to the 200th. Then after it gets that value, it actually raises that value to the 1/200th. So it doesn't multiply the exponents together. It actually applies each exponent separately. And those numbers get so extraordinarily large and so extraordinarily small that the calculator can't handle it. You know, the calculator only goes out how many decimal places? What? 12? I don't know what it is. But it goes out further than that. It's just like, I can't handle this. Kind of like calc students. Okay? So, for your explanation, you want to say your numbers. The calculator, the numbers get too large or small for the calculator to handle. For the calculator to handle. And how come? Because it doesn't use exponent rules. It actually applies the exponents. Okay? Obviously, if this were a test, I would expect you to know that y would equal x, and this would. No matter how big or small, it would still follow that line. But the calculator, which handles those, I mean, I don't expect you to take 4. Like if x is equal to 4, I expect you to say, okay, well, it's 4 to the first. I don't expect you to take 4 and raise it to the power of 200. Figure out what that is. Then take that value and then take it to the 1/200. That would be it. Insanity. And that's what the calculator's basically saying. No, I'm not. It's insanity. Stop it. That's what the calculator's doing. All right, so we have a new equation here, a new function here. But I want to show you an easy way to reset your window to 10 by 10. All right? Now, we've got a triangle still there. Look at that. It's hovering. All right? So, if I turn this on, I don't even know what my window's at. I still have it 10 by 10, but let's say I do 100 by 1,000, whatever. All right? And I want to know 10 by 10, but I don't want to go back and put -10. Someone's like, well, you can just reset the calculator. You can. But if I go to Zoom, and I go to my standard is 10 by 10. So if I hit enter right there, that'll give me back to my 10 by 10 window, whatever I had graphed last. And in the calculator I had that, was it 3 over 2x on this side? And that'll bring it back to 10 by 10. So you don't have to go back there and go -10, +10 by 1, -10, just go right to standard. So why don't you guys graph this function here. Now be careful. Most mistakes are made simply by typing it into the calculator. So be careful. And when I ask you to find the roots, what am I really asking you for when you graph it? The zeros, which are also the solutions, which are also the x. Thank you. The x-intercept, where it touches the x-axis. So on our 10 by 10 grid, I want you to tell me how many zeros we have. After you graph it and it's 10 by 10, put your calculator down and look up, because I don't want you guys to go on ahead. I want them all to go ahead at the same time. Okay?
I think when it's a long function, then you mess up everything.
Yeah, that's the word. Instead of deleting clear air, typing over it first. So just be careful when you type it in. Okay, I've seen some calculators drop. Yeah, graph it. I want you to see the graph on the 10 by 10 grid. We're looking at this aspect right here.
It looks the same.
So look at it. This is what you should have. Ready? It looks like that. It looks like there are 2 solutions. Okay? Now, this is what I want you to do. There might be 2 ways to do this, but I want this to be, your x's, I want you to go from -10 to 10, which we have. But I want you to change your y's from -500 to +500. And you can make them go every 100. You don't got to make them go every once. You see 500 y ticks above, and then 500 ticks. So go from +500 to -500. Yeah, in our window. I'll put this up here. And when you're done, you're going to see what the graph looks like in its entirety. Yeah, I see some people going, oh, okay. It should look something like that.
Yeah, I got that.
Now, there is something that sometimes works in the graph that allows you to see the whole picture without you trying to figure out the numbers. Okay, someone read to me the equation. It's x cubed, correct? What's next?
Minus 1.1 x squared.
What's next?
Minus 65.4 x.
65.4x. What's next?
Plus 129.
Plus 229. Now, if I graph this is still 10 by 10. This is 229.5. Oh, look at the difference in that. So y equals 220, like AJ said, he hates when you go to the end. You know. 229.5. That's it. Okay, graph that. There you go. And there you go. Now, you know I hit zoom. You know I hit zoom standard. Sometimes if you go to zoom and at the bottom of this there's something that says fits. Sometimes it'll fit. It'll change the window so it fits the entire curve. Sometimes it works. Sometimes it doesn't. So if I hit that, let's see. Oh, look at that. Look at that. That's nice. So instead of having to figure out the window where it will fit, just go to zoom fit. Sometimes it works beautifully. Sometimes it's a little off. So we have that. Now, it still looks like there are two roots. I want you to do me a favor. We are going to zoom in right here. Here is obviously one root it crosses. But here, I don't know, does it touch there? Does it dip below and come back? Does it not touch at all? Maybe there's only one root. I want you to zoom extremely close. And I give you your x. I want it to go from 4.95 to 5.15.
Wait, what?
It's on your paper. And your y, I want you to go from negative, that's not -1 to +1, it's -0.1 to +0.1. That is an extreme close-up of this right here.
Wait, so minimum is 1, right?
That's, no, it's -0.1
Oh,
to +0.1. Yes, you're correct. And I hope you're drawing these on your little graphs. That's why I
so what
supplied you
about
the graph.
4.95? That's for the minimum x, right?
The x min is 4.95. The x max is 5.15. For y, your min is -0.1, and your y is +0.1.
Oh my God.
That is an extreme close-up, but what do you notice?
Yeah, I got it.
How many times does it touch the x-axis?
Right?
Yeah, it actually touches it twice. It doesn't look like it here. It looks like it touches twice altogether here. It looks like it touches twice altogether here. It really touches 3 times. How come? Because this touches once here, and when we zoomed in, it actually comes down, then back up. It touches twice here, not once. So there are 3 answers, not 2.
Wait, explain that. Oh, I see it.
Yes. So right here where we zoomed in, okay, like I said, we know it touches once here, but right where we zoomed in here, it doesn't touch once, it touches twice. It dips below, then comes back up. Like that. We just can't see it unless we zoom way in. Okay?